Okay, the next topic is for the parallel RLC circuit. That is, what is the Q factor? Or the relation between the Q factor. Uh, you can see relation between the Q factor. So from the expression, we can write down in the previous expression, that is I equal to V into Y, that is minimum. We have just derived this. Okay. So in this case, we know that is omega L equal to omega C. But this omega C is 1 by omega C. Okay. As Y equal to 1 by R. Okay. At the resonant condition, the resonance condition, we know R became the total impedance, that is the maximum. Okay, and omega L equal to omega C, or we can write this omega coming to here, so we get omega and this L coming to here, so it is become L and C. So omega equal to 1 by root under LC. Okay, this is radian per second. Okay, and if you want to write directly in the frequency format, then we can write frequency is 1 by 2 pi into LC. This is the resonating frequency. Okay. Now we have to remember these things. What are the graphical representation of frequency versus current? Just remember these things. This circuit was just this graph was just like this. So in this part, XL is greater than XC, and in this part, XC greater than XL. Okay, so in this part, I lags V, and in this part, I leads V. Okay, why? Because V equal to IR, I equal to VR, V by R, and omega not omega equal to 0. At the omega equal to 0, then XL equal to 0, and omega and, and same wise we can say that XC is also omega C. So in this way, this is the graphical representation and meaning. Now, what are the relationship with the Q factor? Look, uh, this is omega, this is resonating frequency, and this is your I, and this is I minimum. This is Q3, this is Q3, this is quality factor 2, this is for quality factor 1. You know, from this graph, you can see the quality factor 3 is greater than quality factor 2, is greater than quality factor 1. So you can see this is the quality factor 1. So this is okay. So this is the skewness of the quality factor. Same wise, this is R3 greater than R2 and R1. We will just see this. we'll just see this just now. Okay, so as the quality factor is there, then it is going to the skewness. Okay, better quality factor. Now what is the quality factor? Quality factor, you can see quality factor means 2 into pi into energy stored per cycle and energy dissipated per cycle. So you can write energy stored per cycle, energy dissipated per cycle. Okay, this is the quality factor. So we can also write down this expression just like this. Quality factor stored per cycle by power dissipated. So we can write this half of Li square. This is for inductance, and half of Cv square. This is for capacitance. For inductance, for capacitance. So we can write that Q equal to omega multiplied by C V square RMS by I square RMS into R. Okay, half of will be nullified. Now we can write C into CVR square, CVRMS square, sorry, and this I is V VRMS square divided by R, because this R square and this is R, so it is going down this curve and it yielding you, that is C omega, this cutted omega C, and this R will be coming over here. So this is omega C R. Okay. So Q equal to, we can say Q equal to quality factor equal to R by XC and also R by XL. Okay. So this is the relation between this. So if R is increasing, then its Q is also increasing. So if R3 greater than R2 greater than R1, then its quality factor also differentiate. Okay. So we should go for a numerical so that it became clear. So for this circuit, okay, so find it out. Very simple. Just you have to calculate and you have to put the formula over there. And for the parallel circuit, I think you know, but just do it. Or I will, if you don't or you forget, then I will do this. So what is the formula? Formula is, just remember, this resonant
F
frequency.
equal
Yes, yes.
1.1
One answer is
1.57 radian per second.
and in hertz. It is asked in frequency. Okay, so you have to put rather hertz is better. Are you okay?
Okay, sir.
Look, formula. Which formula you have used?
F equal to 1 by 2 pi root LC wala, sir.
But this is for the parallel. This is series. If you go for parallel, you have to use this type of formula. Okay. Then it will be better. Look, 1 by LC. This is the formula. Look, if you go for the solution, then if you use this formula, then 1 by 2 pi, just put down this 1 by LC. What is the L? L means that is 0.1 Henry. So just 0.1 Henry. And C, what is the C? C means that is 10. 10 microfarads. So 10 into 10 to the power minus 6. Okay, this is LC minus what is the RL? That is R square L, that is R is 10. So this is 10 square by the L square. L is 0.1 and that is square. Okay. So 1 by 2 pi, you can see this is ultimately this item will be going to the upper side, and 1 point into 10, that will be just 1, and 1 to 1, this is 100 square, sorry, 100 divided by 0.1 square means 0.1. So ultimately it will be given this 10. So it will be 10 to the power 6 minus 10 to the power square. You will get 1 by 2 pi into 9.9.8. Okay, and ultimately if you multiply it with this, then we get 158.35. This is the answer. Okay, so this is more or less about the parallel RLC circuit and series RLC circuit.
Sir, there is root under 10 ka power 6 minus 10 ka power 4, I think.
Yeah.
No, sir. After that, equal to 1 by 2. Yes, sir, there. 10 to the power 6 minus 10 to the power 4.
10 to the power 4. No, this is 10 to the power 2, 10 square. Okay, you may check this. But as per my calculation, it is coming here.
सर 0.1 का स्क्वायर है ना नीचे सर, वो ऊपर जाएगा 10 का पावर 4 हो जाएगा सर.
0.1 means look, 0.1 means 0.1 means okay. So 0.1 means another 0. If you put if you cut this, something is doing. Where is it? Not working. I am doing by my mouse, not pen is working over there. 10.1. So 1 point means here is 10. Okay. Then it is 1. Okay. And another point, 1 point means it is another 10. So 2, 2, it is 4. Yes, this is 4. This is 4. Thank you. Okay.
Yes, sir.
Oh, thank you. Anything else? So up to that, it is RLC circuit. Then next classes I will start another thing. Okay, I am going to stop here. Thank you.
Thank you, sir.